안녕하세요. 네. So I have prepared this presentation in English actually, but so I want to know how many people are here want to hear this talk in English. Could you raise up the hand? Not many, but yeah, but for the principle of diversity, I'm going to continue in English. But if I have problems in English speaking, then I may switch it to in Korean for some parts. But anyway, I'm going to continue that. So thank you. So my name is Joongi Kim, and I'm going to give a talk about high-performance networking with Python. So I'm currently working at a small startup company with 3 people, including me, which is Level Up Incorporation. So first, let me introduce my background. So I received PhD in computer science at KAIST just last semester. And I have designed a packet processing framework using heterogeneous processors using CUDA GPUs and Intel Xeon Phi coprocessors. So that was one of the world's first 80 gigabps capable packet processing framework written in pure software, which runs on a single x86 Linux servers. It is composed of about like 48,000 lines of C++. That's kind of very enormous amount of engineering efforts to get high performance in networks. And now I'm working in LabRub, as I said before, as a CTO, developing a distributed sandbox code execution service using Python with 0MQ and async IO library. So in this talk, I'm going to give some introduction to async IO library and other alternative approaches to get even higher networking performance with Python. So the motivation and the goal of this talk is to let you grab some basic understandings and feelings of the key principles for high performance networking. So what do we need to achieve extremely high performance networking in general, and how can we make a balance between the programmability and the high performance using Python async IO library. So this talk is going to be somewhat very technical. So I'm going to assume that you have some basic knowledge about socket programming, some basic experience on writing software applications, even that is very simple ones like Echo Server. And I also assume that you have some basic knowledge on the network stacks like TCP/IP, what is TCP or what is IP, something like that, and some familiarity with Python standard library, and also multi-threaded programming. But even if you don't know about these topics in detail, but I want to give some brief introduction and give you the feelings on how to make high-performance networking programs. So the Python version for this talk is 3.5.2, which is the latest version today. So in this talk, I'm going to give you a brief introduction on the issues, basic issues in networking, and how much your code can get complicated with manual event loop implementation. So yeah, and then introduce the Python solution using generators and converting them into asynchronous coroutines. And then I'm going to also describe several tips to learn and use async IO library, and then how to get high performance with async IO library in general. And then if I have more time at the time, then I'm going to introduce some alternative approach named PyParallel. So the fundamental issues in networking is we can describe in two ways. So networking is basically communication with other people or other computers. Then we need a reliable data communication. So the reliability means that if the network gets disconnected intermittently, even such under such conditions, we should be able to transfer the messages without as the message is sent. And the second thing we need for networking is multiplexing multiple communication channels. So we usually do not talk with only one person. We talk with many persons. So we need some way to organize such multiplex, such complication that arises from having multiple channels. So traditionally, these kind of things have been managed by operating systems or the programming language and runtimes that you use. But here I'm going to show that multiplexing issue must be handled more in an explicit way. So a very traditional problem in networking is the C10K problem. So this is basically to have 10,000 clients served by a single server. So the network systems tries to keep up with many concurrent connections without dropping the throughput and the per request performance. But this problem itself is very simple, but it is very difficult to realize in reality. So because asynchronous I/O requires to rethink your application structures from scratch. So there have been many ways to multiplex network connections in general. So the first category is to create a new parallel context for every new connections. It is simple to write programs using blocking codes, but the disadvantage of this approach is high context switching overhead and high memory consumption. Then people try to design a different kind of API, such as select, POR, ePOR, and KQ. So you get readiness notification from the operating system among a set of file descriptors you want to monitor. Then you can implement handling of multiple different connections within a single thread using this method with much less overhead depending on the underlying kernel implementation. But this makes writing of new programs very difficult. So let me show why that becomes complicated. This is a very simple Python-based event loop implementation of simple echo server. Using readiness notification, you register callback functions to specific network events, such as accept that means there is a new incoming connection, and read means that there is a new data to read from a specific connection. But so I think some of you have heard of the hell of callbacks in JavaScript programming world, and the same thing happens here. Oops. So, for example, you have expected just exactly 1,000 bytes to receive, but what if there are not enough bytes when you got the red notification on read callback? Then you need to keep track of some extra contextual information by yourself. For example, if you write this program program in a block with using only blocking core under a single thread, then you might just loop until you get all the bytes you expect. But this kind of programming adds extra complexity, and this makes bigger problems if in the real-world programs. So the root of programming complexity is that we need to keep track of per connection context. Such context includes the number of bytes sent or received, and what is the remaining bytes to send or receive, and which steps to execute when we get specific amount of bytes. So all those steps must be expressed as a chain of callbacks or some kind of global states. And even more, we have to deal with not only sockets, but also synchronization primitives such as locks and timers, signals, which is often expressed as special callback functions that is executed by the operating system. And also communication in sub-processes such as IPC. And even there are some non-standard asynchronous I/O events. For example, if you use like CUDA library to execute complex computations on GPU, you may want to know when the computation is finished in GPU, because GPU is completely kind of black box in the view of the CPU. So so CUDA provides an API that calls stream callback, but this callback interface is not integrated into the operating system, so you just cannot use like file descriptors to monitor such events. So current operating system actually do not provide a unified abstraction to get notifications from all these different kinds of events. So what people are trying to do is to embrace coroutines. So the original concept of coroutine is by definition is cooperative routines. So it's kind of stoppable and resumable functions. So you can think that your program just stops in the middle and it can resume later. But differently from preemptive kernels in operating systems, all the stopping action is done at explicit point I set. So combining this concept of coroutine with an event loop scheduler, Python, C#, and C++, and many other languages are introducing new asynchronous I/O libraries today. The disadvantage of this approach is that naturally, your programming language should support it, because stopping the function and resuming a function should be supported in the language level. But fortunately, Python have done this from very far past. And in Python 3.4, we now have an asynchronous I/O library using that feature. So Python's async I/O library is based on the PP 3156. So PP documents are like a kind of standard documents that describes a specific feature or functions or intention, syntax of Python language. So the motivation and goal of this Python async I/O library is that there already have existing solutions, but they were not enough to satisfy the programmers. So other libraries, including both standard and third parties, they have inextensible APIs and has lack of compatibility. So if we choose to use G event, for example, or twist it, then the whole program must be structured along with that library, and later we cannot replace the underlying implementation even though we discover some problems. So the designers of Python async IO library, they try to make the interface to be general enough to reuse and extensible with pluggable underlying implementations. And they also adopted some good ideas from existing third-party libraries, such as Twisted. So historically, Python have supported generators, which you can stop a function and send a value to the caller of that function, and later resume and continue the execution of that function. So it's now very universally used in Python 3. So for example, the built-in range method is changed to generators in Python 3. And in Python 3.3, we have a new feature called generator delegation, which allows transparent two-way communication between the caller of a generator and another generator called inside the generator. I will explain more details about this later. And Python 3.4 has an event loop integration with such generator delegation, and now they provide a standard package called async IO. In Python 3.5, they have added new syntactic sugar to easily write asynchronous functions. So why do we use asynchronous IO? The idea behind async IO is that overlapping blocking IO requests can reduce total execution time. So as the figure shows here, if we have a long waiting time for a specific IO course, such as socket read, and then we can actually multiplex different IO waits even within a single thread, because underlying hardware and operating system can actually multiplex the multiple different IO connections without intervention of the user process. So the idea is to less exploit that capability of underlying systems in high-level languages like in Python. But I heard that there was another session that was about async IO, and is it really better to async, or do you really want to be async? So anyone have heard that session before here? Yeah, so async IO is a new technology, and you may think, oh, if I use async IO, then my application will be faster. But in most cases, you don't get performance improvements, because you need to get high performance. You need to satisfy several assumptions which underlies in async IO. So, for example, if the IO is so efficient, so the computation time of your program dominates the total time, then you won't get performance improvements, but performance drops actually, because extra context switching overheads between coroutines. And you have enough number of IO channels to wait in concurrently. For example, if you have just only one single socket and then using async IO just introduce more overheads. So you need to think about your application before you move to async IO. And then the advantage of async IO in Python is that despite of the performance overheads introduced by coroutine context switching, single-threaded Python apps are likely to get performance gains if they satisfy such assumptions. And even without performance improvements, if your application have to deal with multiple different kind of asynchronous notifications, such as timers and signals, then you can benefit from the unified abstraction that Async.io provides. So to understand how Async.io works, you first need to understand generators. So the left top code is how we use generators in Python. So I think you all know the range function, the built-in range function in standard library. And this is how we implement that in generator function or generator class. So I'm going to skip the details of this code here. And if we change this to an asynchronous version, then we add async cure to the synchronous to generators to make it coroutines. And we should add an explicit declaration of event loops. Actually, the current Python does not support async generators, but we can use the async generator protocol version. And the concept of generator delegation I mentioned before is another key concept to understand Async.io operation. So the new keyword in Python 3.5, await, is almost same to yield from that is also added in Python 3.3. So how many of you are familiar with the Python 3.3 or higher versions? Have you ever used such versions? No, everybody is still in Python 2 land. Okay. I personally strongly recommend to use Python 3 because at first time you might experience many like Unicode encoding, decoding errors, and I know that is painful, but if you step over that hurdle, then you will enjoy much better consistency between standard libraries and the language itself. And also new features like coroutines. And so basically, await is same to yield from, and with a small difference that handles stop iteration exceptions differently. So this generator delegation keyword allows transparent two-way communication between the coroutine scheduler, usually the caller of my coroutine, and another coroutine that is called from my coroutine. So in the next slide, I'm going to show an example. So if I execute an event loop, then with the coroutine here, for example, compose items, then the coroutine is executed automatically by the event loop. And so the caller of this event loop is the event loop. The caller of this coroutine is the event loop, and this coroutine again calls another different coroutine called fetch data. So in fetch data, that function may have multiple breakpoints, so that stop its own execution and resume its own execution depending on the implementation. For example, we could fetch data from a database or another web server, for example, and we may need different times of explicit stops in that function. But as a caller of the function, the compose items, it is not interested in how fetch data works. It just wants to the final result of the function. So this kind of interaction is done automatically, and the event loop may want to stop the execution of the whole system because the user have pressed Ctrl+C to stop the program. In such case, an exception is injected inside to fetch data without intervention of compose items. So this kind of interaction is called generator protocol, and it is very difficult to describe all the details of the generator protocol in this place, but so that involves various edge cases to handle exceptions and two-way communication between the subcoroutines and the color of coroutines. So all of these things are automatically handled by the Python interpreter if we use await or yield from keywords. So I'm going to introduce some key things to know when you learn about async I/O. So when I first started to use async I/O, I actually had a lot of problems and had many time to pulling my hair out. So basically, you need to know that there are two ways of executing subcoroutines. So one is to non-blocking one. So you execute a coroutine in kind of background, similar to a background process. So that those functions returns immediately in the view of your own coroutine, or you can wait until the subcoroutine finishes just like a normal function call. So this method can only be applied to coroutines. So always you need to always keep track of which functions are coroutines or not when you use a third-party library and async I/O library. Also, please remember that coroutines are not running in parallel because it's executed in a single thread. So they are basically non-blocking and interleaved manually upon await keywords. And so you need to avoid the long-running and non-cooperative blocking calls in coroutines. So this is actually quite a big barrier when you first use async I/O library, because if you are going to organize your program using async I/O, then every library you use must be cooperative with async I/O. And also you need to explicitly call cancel task or loop.stop to interrupt a coroutine, because there is no way to preempt or inject exceptions into a coroutine by yourself. And so I'm going to introduce some tips here, but as the time is going to running out, so I'm going to just skip this part. So just please have a look on the slides. So the one thing I'm going to step over here is that actually debugging coroutines and event loops are very difficult, because if something, so when I write a program, I have expected specific things happen, but it does not happen and just stops there like a freeze computer. But there is no way to which part is actually blocking the whole program. So to remedy this problem, Python provides a various debugging options for async library. So for details, please consult the documentation. So, but you need to know that there are explicit debugging facilities provided by the async I/O library designers, and you can use that. And another tip is that when you write unit tests of asynchronous functions, then you can simply wrap the asynchronous functions with an event loop. But the thing you need to care about here is that you need to create and destroy the event loops every time, every test cases, to ensure complete isolation between different unit tests. So because if we reuse a single event loop for multiple test cases, there may be some case that uncleaned coroutines may corrupt the execution result of other test cases. So this is kind of a tip. And another tip is that you could so when you try to write your program with async IO, I said that you need to find the library that supports async IO. So fortunately, there are some group of people who are writing async IO version of many existing libraries, such as Redis client, HTTP clients, and MySQL clients, and so on. So first, this is the first place to look when you want to write your program in async IO. Also, if you want to implement your own async IO aware libraries, you could look into the source code in here and see how they implement the customized event loop waiting functions. So this is the I think the main probably the main theme of my talk. So how to get high performance with async IO. So the first and the most important thing is that you need to avoid frequent context switching. For example, polling. It may bring very huge difference. I will show the numbers later. And the second thing, avoid as much as possible writing IO logic in Python. So we all know pure Python loops are very slow. So that's why we use NumPy and so many other like calculation libraries to calculate fast. And it's very likely to add unwanted extra memory copies if you use pure Python code. So for example, network packet receiving code, as I shown before, it has a lot of overheads. And in my micro benchmark, the performance is worsened by like more than 5 times. And this is a small tip. So if you want to really extract more performance with async IO, then consider to implement your program with async IO protocol subclasses instead of coroutine-based stream APIs. So in my trials, it may add like 0 to 5% of throughput, more throughput. But I don't recommend to do this because the reason to use Python at the first place is that we want to make programs easier. So I don't recommend this method in fast prototyping. And another thing is that please keep your libraries up to date because the ecosystem for Python asynchronous IO libraries are under active developments. Okay, so this is a simple micro benchmark I used to decide which 0MQ library I should use for our product. So I compared different 0MQ wrapper libraries and different event loop implementations. The workload is a simple producer-consumer patterns. And so the baseline is here, and I compared different event loop libraries. And the performance difference was very dramatic. So at first time I wrote the benchmark, I had a redundant polling loop in my code, and when I published this benchmark repository and notified the author of Py0MQ committer, and he came back and said, you have the wrong code, because and said you have redundant polling. So removing that mistake, the performance got like 2 times better. And that committer has patched his own library to get even more performance. So in the original library, whenever the data comes in, it first enqueued the notification. But this time, if it has the data when it received the notification from the underlying operating system, that it processed that data immediately without queuing. So this change has improved the performance about 5 times. So this small case shows that managing the context switching overheads is critical to achieve high performance. So if you want even more performance, you could try many different things listed here. And this is about like if you want even more performance. For example, if you want to keep up with like 10 gigabps network cards. So such condition is actually very harsh, and even the latest Linux kernels have problems with problems to keep up with this performance. So even kernel can't do that very well. Could Python do it well? So and actually 10G network cards are now deployed on all over the AWS region. So we need to think about it. In the system programmer's perspective, there are many requirements to keep up with such high-speed networks. So we need, for example, zero copy, and we should not use malloc, and we should not use any kind of synchronization primitives and so on. So the key principles are batching, pipelining, parallelization of your network requests. So in Python, I have seen a very interesting alternative approach to async I/O, which is called PyParallel, which focuses on parallelization. So this is a screenshot from the PyParallel homepage, and it says that it supports very high performance processing. So in Python, we all know the GIL, Global Interpreter Lock, limits the performance in parallelization. So, so how do we remove or work around that GIL limitation? So PyParallel did it very well. So it supports the performance of Node.js and Go Go servers, and so the developer has approached the problem in completely different way. So he used a completion-oriented I/O provided by Windows. So PyParallel only works on Windows, but it used the IOCP, which is a OS operating system managed APIs that offers high-performance networking. So yeah, I'm going to skip the details about the concepts here. So he had separated the parallel context and the normal context in C/Python interpreter. So they patched the Python interpreter and built a customized one. And in parallel context, it uses very optimized version of memory allocators, reference counters, and so on. In normal context, it uses just the C/Python code as it is. So in this way, it could keep the compatibility with most Python libraries. And under parallel context, it could run without GIL limitation. There are many technical details here, so I recommend you to look the slides released by the authors in their webpage. And code looks looks similar to async I/O, so you could try it easily. Yeah, so PyParallel is a very interesting alternative approach, I think. So to summarize my talk, async I/O offers a sweet spot between programmability and high performance in networking with Python. So the main advantages come from coroutines enabled by generator and generator delegation features. And it allows clean separation of event loop implementations and the event loop users. So the plug-over event loop has allowed high-performance third-party libraries such as UV loop. And for even more performance to fully exploit multi-core systems, we actually need to rethink the whole stack of networking. So from the operating system, drivers, kernels, as well as the user space abstractions, including Python and the GIL stuffs. So, and PyParallel is a very interesting example, even though it is only implemented on Windows. So I'm very curious about what kind of alternative approaches will be available in the future, and I want to see your suggestions and discussions on this asynchronous I/O topic here. So, okay, let me conclude this talk. And I will, after Q&A, brief Q&A, I will be on the OST room 209. So please come there and talk with me. Thank you.